Hey everybody, welcome back. Tonight we are going on a proper deep dive, almost 2 full hours, into one of the weirdest, most stubborn little choices in the entire history of science. It's a unit of distance called the parsec. Here's the crazy part. Almost no star in the known universe is exactly 1 parsec away from Earth. Literally almost none. And yet, if you open any professional astronomy paper written in 2025, any catalog, any conference talk, any grant proposal, you will see distances in parsecs, kiloparsecs, megaparsecs, sometimes gigaparsecs. It is absolutely everywhere. It is the default unit of professional astronomy, and it has been for almost 2 centuries. By the time we're finished tonight, you're not just going to know what a parsec is, you're going to understand the full, wild, 187-year backstory of how a measurement decision made by one obsessive German guy in 1838 accidentally created a unit that still completely dominates the field today, even though it makes basically zero intuitive sense to anyone who isn't a professional astronomer. If that sounds fun, buckle up. Let's start at the very beginning. Short musical sting. Imagine it's the winter of 1837. You're standing outside in the freezing cold of northern Germany, night after night, staring up at a faint little star in the constellation Cygnus, called 61 Cygni. You know the Earth is screaming around the sun at nearly 67,000 miles per hour. And if you are patient enough, precise enough, obsessive enough, you might, just might, catch that star shifting ever so slightly against the background of much more distant stars as the Earth changes its vantage point in orbit. If you can measure that tiny shift, you will have done something humans have been trying and failing to do for 2 full millennia. Measure the actual distance to a star. One man finally did it. His name was Friedrich Wilhelm Bessel. And what he could not possibly have known in 1838 was that the geometry of his breakthrough measurement would accidentally create a unit of distance that still rules astronomy almost 200 years later. A unit that marks no natural boundary in space, a unit that no star actually sits at, a unit based purely on the details of how he took his data. That unit is the parsec. For almost all of human history, the distance to the stars was a total blank. The ancient Greeks cataloged over 1,000 of them. Hipparchus around 130 BCE measured their positions incredibly carefully, tracked their brightness, watched them move across the sky. But distance? They had zero clue. Their best model was that every single star sat on a giant crystal sphere just beyond the planets, all exactly the same distance from Earth. And honestly, that wasn't stupid. It was the best model that fit the observations they had. The stars looked like perfect, fixed points of light that never, ever moved relative to each other. The constellations looked identical night after night, year after year, century after century. The Greeks even had a word for this giant dome, the firmament, from the Latin word, meaning to make firm or strengthen. They thought the stars were literally embedded in a solid crystalline sphere that spun around the Earth once a day. Aristotle argued this sphere had to be made of a 5th element, completely different from earth, water, air, and fire. He called it ether or quintessence, perfect, unchanging, eternal. The stars shared in that perfection. They never changed. Brightness never appeared or disappeared, never moved except for the daily rotation of the sphere itself. That model lasted 2,000 years because no instrument existed that could prove it wrong. The stars really did look absolutely fixed to every telescope built before the 19th century. Telescopes finally arrive in the 1600s. Galileo sees mountains on the moon for moons orbiting Jupiter and realizes the Milky Way is made of countless individual stars. But the distance question, still nothing. The stars refused to budge. To measure distance, you need parallax. You have to see the object from 2 different vantage points and measure how much it appears to shift. That's how your brain does depth perception. Your eyes are only 6 centimeters apart. Good enough for things a few meters away, useless for stars. So astronomers realized Earth orbits the sun. That gives us a baseline almost 300 million kilometers across 186 million miles. Observe a star in January from one side of the orbit, then again in July from the opposite side. You're now looking through eyes separated by 300 million kilometers instead of 6 centimeters. Even the nearest stars should show a tiny shift against the background. That shift is called stellar parallax. Conceptually, it's dead simple. Draw a giant triangle. The base is the diameter of Earth's orbit, 2 astronomical units. One vertex is the star. Measure the angle at the star, use basic trigonometry, solve for the distance. High school level geometry. In practice, it was absolutely brutal. The angles are smaller than 1 arcsecond. 1 arcsecond is 1/3600th of a degree. A tennis ball held 1 kilometer away appears about 1 arcsecond wide. A person standing on a ship 10 kilometers out at sea is about 1 arcsecond tall. 17th and 18th century telescopes couldn't come anywhere close to that precision. Atmospheric turbulence blurred everything by several arcseconds. Temperature changes made telescope tubes expand and contract. The astronomer's own heartbeat could jiggle the eyepiece. Wind, building settlement, everything conspired against you. People tried anyway. 1669, Robert Hooke, one of the most brilliant experimentalists England ever produced, the guy who literally discovered biological cells and gave us Hooke's law of elasticity, builds a giant vertical telescope in a tall building to get above some of the shaky air near the ground. He spends months measuring the bright star Gamma Draconis and announces to the world that he has finally detected stellar parallax. He was wrong. What he actually discovered was stellar aberration. The combination of light's finite speed and Earth's orbital motion makes every star appear to trace a tiny circle in the sky every year. It's a real effect, but it's not parallax. James Bradley properly explained it in 1728 and got the credit. Then comes William Herschel, the guy who discovered the planet Uranus in 1781 and instantly became famous overnight. He tries a completely different trick in the late 1700s and early 1800s. He looks at double stars, pairs that appear close together in the sky, and figures that in some of those pairs one star must be much closer than the other. So the near one should show parallax while the far one stays put. He measures thousands of double star separations over decades with insane patience. Result? No parallax. But again, the failure wasn't wasted. Herschel accidentally discovered that most of those doubles aren't just chance alignments. They are real binary systems physically orbiting each other under gravity. That turned out to be one of the most important discoveries in all of stellar astronomy, because binary stars let us weigh stars using Newton's laws. By the early 1800s, measuring stellar parallax had become astronomy's ultimate white whale. Everyone knew it had to be possible in principle, but nobody could actually do it. Dozens of the best astronomers in Europe spent years on the problem. A few claimed success, published numbers, but nobody else could reproduce them, and the claimed distances were all over the place. Then came Friedrich Wilhelm Bessel. Bessel didn't even start life as an astronomer. Born 1784, he began as an accountant for a shipping company in Bremen. In his spare time, he taught himself mathematics and celestial navigation so well that at age 20, he recalculated the orbit of Halley's Comet from old observations, purely as a hobby, and did it so accurately that professional astronomers noticed and basically said, "Kid, come work with us." By age 26, he was director of the brand new observatory in Königsberg, Prussia, where he would stay for the rest of his career. Bessel was different from everyone who came before him. He was obsessed with precision and error analysis at a level that was almost unheard of in the 1830s. While most scientists of the era just wrote down whatever number their instruments spat out, Bessel treated every measurement like a crime scene. He wanted to know every possible source of error and quantify it. Temperature changes making the brass telescope tube expand or contract by a millimeter. He glued thermometers directly to the tube and created correction tables. Atmospheric refraction bending. Starlight differently depending on temperature, pressure, and humidity. He measured it night after night and wrote mathematical formulas. Tiny mechanical play in the telescope mount that changed, depending on whether it was pointed east or west. Modeled even the slow settling of the observatory building's foundation over months. He tracked it. In 1837, he finally decides the time is right. He picks his target very carefully. 61 Cygni. It's not bright, fifth magnitude, right at the edge of naked eye visibility under perfect dark skies. But it has the largest known proper motion of any star at the time. Proper motion is how fast a star appears to crawl across the sky over years and decades. High proper motion usually means nearby, the same way cars in the near lane on the highway look like they're going faster than the ones far away. Bessel uses a brand new instrument called a heliometer. Picture a telescope whose front lens is literally cut in half. You can slide the two halves past each other by tiny amounts and create two overlapping images of the star field. By measuring exactly how far you have to slide the halves to make one star's image land on another, you can measure angular separations down to 1/10 of an arcsecond, cutting edge for 1837. From August 1837 to August 1838, he observes on every single clear night hundreds of measurements. He doesn't try to measure 61 Cygni's absolute position, because the telescope itself might shift a little. Instead, he measures its angular separation from several very distant background stars that should have essentially zero parallax. Every night, separation to reference star A, then B, then C over and over and over. As Earth swings around the Sun, 61 Cygni slowly traces out a tiny ellipse against those fixed background stars. The size of that ellipse is the parallax. But the real parallax signal is absolutely buried under dozens of effects, each one dozens or hundreds of times larger than the thing he's trying to measure: atmospheric refraction that can shift a star 30 arcseconds near the horizon, temperature expansion of the telescope, the 20 arcsecond aberration of light, gravitational flex in the mount, the slow precession of Earth's axis, everything. Bessel spends months after the observations correcting for every single one, by hand, using logarithm tables, because calculators won't exist for another 100 years. Finally, he isolates the parallax, 0.3136 arcseconds. That is an angle roughly the width of a human hair seen from 100 meters away, or the width of the period at the end of the sentence if you're looking at it across a football field. Using basic trigonometry, he gets a distance of about 10.3 light-years. Modern measurements with space telescopes say 11.4, so he was within 10%. With 1838 technology, that is absolutely mind-blowing. Within months of Bessel's announcement in late 1838, the floodgates just burst open. First, Thomas Henderson, a Scottish astronomer working at the Royal Observatory at the Cape of Good Hope in South Africa, suddenly remembers that he actually measured Alpha Centauri back in 1832 to 1833. He had seen a shift that looked like parallax, but he was so cautious, maybe too cautious, that he sat on the data for years worried about systematic errors. The moment Bessel's paper lands in early 1839, Henderson realizes his own measurements were legit and rushes to publish. Alpha Centauri turns out to be even closer, about 4.4 light-years. So technically Henderson made the first actual observations, but Bessel gets the historical credit because he published first. Science is brutal that way.
10 Friedrich Georg Wilhelm von Struve at Dorpat Observatory, now Tartu.
Estonia publishes a parallax for Vega shortly after. Vega is much farther, about 25 light-years, so the angle is tiny and the measurement is less accurate, but it's still a real detection. Suddenly, after 2,000 years of nothing, we have solid distances to 3 stars, and more are pouring in. Within a few years, astronomers have dozens of parallaxes, by the early 1900s hundreds, by the mid-20th century thousands. Every single one confirms the same mind-blowing fact. The stars are scattered across absolutely insane distances, far beyond anything in the solar system. Alpha Centauri, the closest, is 270,000 times farther than the Sun. Sirius, one of the brightest stars in the sky, is twice as far again. The universe just got a lot bigger. But now astronomers have a practical problem. How do you talk about these gigantic numbers without writing 97 trillion kilometers every 5 seconds? Saying a star is 657,000 astronomical units away is clunky. Light years help a little, but they're still not ideal for day-to-day work. So history isn't totally sure who first suggested it. comes up with a beautifully simple idea. Why not define a brand new unit that comes straight out of the parallax measurement itself? Here's how it works. Take a right triangle. One leg of the triangle, the base, is exactly 1 astronomical unit. The average Earth-Sun distance. The angle opposite that base at the star is exactly 1 arcsecond. Solve for the long side of the triangle, the hypotenuse. That is the distance to the star. Using basic trig, that distance turns out to be about 206,265 astronomical units, or roughly 30.9 trillion kilometers, or about 19.2 trillion miles. They called this distance 1 parsec, a contraction of parallax and arcsecond. The name literally tells you how it's defined. Now here's the crucial thing. 1 arcsecond was chosen purely because it's a nice round number in the angular system humans have been using for thousands of years. The Babylonians divided the circle into 360 degrees because 360 has tons of factors. They split degrees into 60 arc minutes and arc minutes, into 60 arc seconds because 60 is also highly divisible. This is why we still have 60-minute hours and 60-second minutes. This pure historical convenience, nothing physically special about it. An alien civilization that divided circles differently might have a completely different angular unit and therefore a completely different parsec. The parsec is 100% a human cultural artifact. And almost no star actually sits at exactly 1 parsec. Proxima Centauri, our closest neighbor, is 1.302 parsecs. Sirius is 2.64. Vega is about 7.7. Bessel's 61 Cygni is roughly 1.03. There's no magic sphere at 1 parsec where physics changes. It's just the distance that makes the math convenient. But that convenience turned out to be massive. For working astronomers who are measuring parallaxes every day, the parsec has one killer advantage. Distance in parsecs is literally just 1 divided by parallax in arcseconds. Parallax 0.5 arcsec distance 2 parsecs. 0. 25 arcsec 4 parsecs. 0.1 arcsec 10 parsecs. 0.05 arcsec 20 parsecs. No calculator, no conversion factors, no looking up tables, just flip the number. When you're processing hundreds of measurements by hand, which is what astronomers did for decades, that directness is gold. Imagine you're sitting there with a notebook full of observations. Star A, 0.15 arcsec OK, about 7 parsecs. Star B, 0.283.6 parsecs. Star C, 0.0812.5. You can do it in your head while you work. Make a mistake and accidentally measure 0.5 instead of 0.05. You get 2 parsecs instead of 20, and you instantly know something went wrong because that star would suddenly be one of the closest in the sky and you'd have noticed. Using kilometers, you'd have to multiply by some huge number every time. Astronomical units, divide by 206,265 every time. Light years, multiply by 3.26 every time. Every extra step is another chance for arithmetic errors. The parsec eliminates all of that. By the late 1800s, astronomers are using it in papers because it makes their lives easier. Other astronomers read those papers and adopt it because the numbers are cleaner. Catalogs start listing distances in parsecs. Textbooks explain it. By 1900, it's the default unit for stellar distances in professional astronomy, not because some committee voted, but because it was genuinely the most practical choice for the people actually doing the work. And then the universe just keeps getting bigger. Podcast script, part April 15th.
7,859 ký tự chính xác.
Host, voice picking up pace, building excitement. As telescopes get better in the early 20th century, astronomers start measuring parallaxes for stars hundreds, then thousands of parsecs away. Writing 3,000 parsecs over and over gets old fast, so they do what humans always do. They borrow the metric prefixes. 1 kiloparsec equals 1,000 parsecs. A typical globular cluster is maybe 15 kiloparsecs away. The center of the Milky Way is about 8.2 kiloparsecs from us. Then, in the 1920s comes Edwin Hubble's bombshell. Those fuzzy spiral nebulae that astronomers had been arguing about for decades, they're not gas clouds inside our galaxy. They are entire other galaxies, island universes, billions of stars, each millions of times farther away than anything we'd measured before. Hubble figures this out using Cepheid variable. Stars in the Andromeda Nebula. Henrietta Leavitt, one of the legendary Harvard computers, had discovered in 1912 that Cepheids have a rock-solid period luminosity relation. The longer a Cepheid pulsates, the intrinsically brighter it is. Measure the period, know the true brightness, compare to how bright it looks distance. Hubble finds Cepheids in Andromeda, measures their periods, does the math, and gets roughly 280 kiloparsecs. Modern value is about 780 kiloparsecs, so he was off by a factor of almost 3, but it was still clearly way outside the Milky Way. Andromeda becomes the first external galaxy with a solid distance. Writing 780,000 parsecs over and over is annoying, so astronomers invent the megaparsec, 1 million parsecs. Andromeda is 78 megaparsecs away. The Virgo cluster is about 16 megaparsecs. The Coma cluster is roughly 100 megaparsecs. Hubble then discovers that the farther away a galaxy is, the faster it's receding, and the relationship is perfectly linear. That's the famous Hubble law, and it proves the universe is expanding. As observations push deeper, we need gigaparsecs, 1 billion parsecs. The edge of the observable universe is roughly 14 gigaparsecs in comoving coordinates. We took a unit originally invented for nearby stars and just kept slapping bigger prefixes on it because the universe refused to stop getting larger. At every step, the parsec stuck around because converting everything to a new unit would have been more work than just adding another prefix. All the formulas, all the catalogs, all the mental habits were already in parsecs. Switching would have required a massive coordinated effort across the entire field for very little gain. But the real reason the parsec became absolutely foundational, not just for nearby stars but for the entire cosmic distance ladder, is what happened in the early 20th century when astronomy went from one guy with a telescope to massive systematic surveys producing oceans of data. Starting in 1877, Edward Pickering at Harvard decides to photograph the entire sky, north and south hemispheres. Over decades, they take 500,000 glass plates, each one holding thousands of stars. Someone has to measure positions, brightnesses, classify spectra. That's way too much work for a handful of professors. So Pickering hires a team of women, pays them basically nothing, and calls them computers, because their job is to compute. These women, despite getting almost no credit at the time, make some of the biggest discoveries in astronomy history. Annie Jump Cannon classifies over 350,000 stellar spectra and invents the OBAF-GKM sequence we still use. Williamina Fleming discovers hundreds of variable stars and novae. Cecilia Payne-Gaposchkin figures out that stars are made of hydrogen and helium. But for our story, the most important is Henrietta Swan Leavitt. Leavitt is studying variable stars in the Magellanic Clouds, 2 small satellite galaxies visible from the southern hemisphere. She notices a particular type called Cepheid variables that pulsate, with perfectly regular periods. In 1912, after years of measuring plates by eye, she publishes the period luminosity relation. Longer period equals intrinsically brighter, and the relation is tight and predictable. This is huge. Find a Cepheid anywhere, measure its period, you instantly know its true brightness. Compare to apparent brightness distance. Cepheids become standard candles, and they're genuinely bright, thousands of times brighter than the sun, so you can see them across millions of parsecs with big telescopes. Suddenly, distance measurements jump from a few hundred parsecs, the limit of ground-based parallax, to millions of parsecs. But, and this is the key point, to calibrate the period luminosity relation, you need to know the actual distances to the nearest Cepheids. And the only way to get those distances is parallax, or statistical methods that ultimately trace back to parallax. So the entire cosmic distance ladder, everything we use to measure the size and age of the universe, rests on parallax distances measured in parsecs. Parallax nearby Cepheids in parsecs calibrate the period luminosity relation Cepheids in distant galaxies in megaparsecs calibrate type Ia supernovae out to gigaparsecs. Every single step is anchored to the parsec. That's why the unit spread everywhere. It's not just convenient for nearby stars. It's the bedrock of literally all astronomical distance measurements. Podcast script, part May 15th.
751 ký tự chính xác.
Host, voice softening a little, almost conspiratorial. Now here's where the story splits into two parallel universes that still exist today. Professional astronomers embraced the parsec completely and universally. Every research paper, every catalog, every technical talk, parsecs, kiloparsecs, megaparsecs, no debate. But the moment you step outside the ivory tower, the moment you try to talk to regular human beings, something very different happens. The 1950s and 60s bring the space race. Sputnik, Yuri Gagarin, Apollo 11. Suddenly hundreds of millions of people want to learn about the cosmos. Popular books explode onto the market. Magazines, TV shows, planetariums, everything needs to explain astronomical distances to non-experts. And every single one of them uses light years, not parsecs. Carl Sagan's Cosmos in 1980 is probably the single most influential science series ever made. Over 600 million people watched it in 60 countries. Sagan talks about Alpha Centauri being 4.24 light-years away, the Milky Way being 100,000 light-years across, distant galaxies being millions or billions of light-years away. He never once says the word parsec in 13 episodes. Not once. And it makes perfect sense. The light year is self-explanatory. Light is the fastest thing in the universe. Everyone knows what a year is. Put them together and you instantly get a really long distance, and you also get the poetic bonus that when you say Andromeda is 2.5 million light-years away, people immediately understand we're seeing it as it was 2.5 million years ago, back when our ancestors were just figuring out stone tools. That hits you in the chest. Try that with parsecs. Andromeda is 0.78 megaparsecs away. Cool, what does that mean? You have to stop and explain parallax, arcseconds, Babylonian base 60, the whole thing. Kills the magic. So a split emerges that is still 100% alive in 2025. Inside the professional community, parsecs only. Outside, in every newspaper article, every documentary, every museum exhibit, every TikTok astronomy video, light years only. Same astronomer, same galaxy, two completely different numbers depending on who they're talking to. Write a paper for the Astrophysical Journal? The galaxy is at 300 megaparsecs. Same person interviewed by the New York Times about the same galaxy? It's roughly 980 million light years away. Creates this weird bilingual situation. People who read popular books think in light years. Then they take an intro astronomy class or try to read a real paper and suddenly everything is in parsecs, and they have to keep converting in their head using 3.26. It's a genuine barrier. But both sides have totally legitimate reasons. Professionals aren't being snobs. Their entire software, databases, and mental math are built around parsecs. Switching would be like asking the entire field to rewrite millions of lines of code and retrain their intuition overnight. Popular communicators aren't dumbing anything down. They're just choosing the unit that actually lands with human beings. And then, starting in the late 20th century, something happens that cements the parsec's dominance. For probably another century, space missions whose entire purpose is to measure parallax better than ever before. The granddaddy of them all is Gaia, launched by the European Space Agency in 2013. Gaia's goal is insane. Measure precise positions, distances, and motions for over 1 billion stars, roughly 1% of the entire Milky Way. It has two telescopes pointed 106.5 degrees apart, constantly scanning as the satellite spins and precesses. For bright stars, it measures positions to a few microarcseconds. That's a millionth of an arcsecond. That's like measuring the width of a human hair from 1,000 kilometers away. By its final data release in the early 2030s, Gaia will have measured parallaxes for stars out to several kiloparsecs for bright ones and hundreds of parsecs for typical stars. That is orders of magnitude farther and more precise than anything ground-based telescopes could ever do. And every single distance in the Gaia catalog is reported in parsecs, not because of tradition, because Gaia literally measures parallax in arcseconds. Distance equals 1/parallax. It is the natural unit. Converting to anything else adds an extra step and an extra place to make mistakes. The entire multi-billion euro data processing pipeline was built from day one assuming parsecs. All the analysis tools, all the databases, everything. Gaia alone has probably locked the parsec in for at least another 50 years. And Gaia isn't alone. Hipparcos before it, the upcoming Roman Space Telescope, the Rubin Observatory, all of them either measure parallax directly or rely on parallax-calibrated standards. The infrastructure just keeps growing. Gaia also showed us something beautiful about the parsec definition itself. The simple 1838 version Bessel would have recognized 1 AU subtending 1 arcsecond has quietly evolved. Modern parallaxes have to correct for things Bessel never dreamed of. Earth's orbit isn't a perfect circle. It's slightly elliptical. Jupiter and Saturn tug Earth around a little. The Moon makes Earth wobble as the Earth-Moon system orbits their common center of mass. And, thanks to Einstein, starlight grazing the Sun gets bent by general relativity by about 1.75 arcseconds, which is actually larger than many of the parallaxes Gaia measures. So the straight line, flat space, Newtonian triangle from 1838 is officially an approximation. The International Astronomical Union updated the exact definition in 2015 to include all the relativistic and orbital corrections, but the basic idea is still the same. 1 parsec is the distance at which 1 astronomical unit subtends 1 arcsecond, just with all the grown-up corrections baked in. The official modern value is exactly 3.26156378 light-years, or about 30.857 times 10 superscript 1 kilometers. Let me give you some gut-level feel for how absurdly huge that is. The fastest human-made object ever is NASA's Parker Solar Probe. At closest approach to the Sun, it hits almost 700,000 kilometers per hour, about 0.0006 c. At that speed, it would still take roughly 5,100 years to cross 1 single parsec. Proxima Centauri at 1.3 parsecs would take Parker about 6,600 years. Sirius at 2.64 parsecs, 13,500 years. Even the Alpha Centauri system, the closest star system proper, would be over 6,000 years away. These aren't science fiction numbers. These are the real, brutal limits of chemistry and gravity assists. Even if we ever build nuclear rockets that reach a few % of light speed, Proxima is still a century-plus round trip. The parsec isn't just a unit. It is a constant reminder of how isolated we actually are. But it's also the key that unlocks almost every major diagram and equation in stellar astrophysics. Take the Hertzsprung-Russell diagram, the single most important plot in the field. Horizontal axis, temperature or color. Vertical axis, luminosity, true power output. To place a star on the vertical axis, you need to know its true luminosity, not just how bright it looks from Earth. And apparent brightness depends on both luminosity and distance. A faint star close by can look exactly as bright as a blazing monster far away. To turn apparent brightness into true luminosity, you need distance. Period. Astronomers define absolute magnitude as how bright a star would appear if it were placed at a standard distance of exactly 10 parsecs. Why 10? Because 10 is a nice round number, and when distance is in parsecs, the conversion formula is gorgeous and simple. Absolute magnitude equals apparent magnitude minus 5 times log distance in parsecs plus 5. That plus 5 at the end comes directly from the 10 parsec standard. If you tried to use light years, the formula instantly becomes Messier because you have to divide by 3.26 somewhere. Do that for thousands of stars by hand and you will make mistakes. The parsec makes the HR diagram clean, which means generations of astronomers learn to think. in parsecs before they even realized they were doing it. The same thing happens with the cosmic distance ladder.
Rung 1. Trigonometric parallax direct geometric distance, pure trig.
No physics assumptions out to a few thousand parsecs with Gaia. Rung 2. Spectroscopic parallax. Terrible name. You take a spectrum, figure out what type of star it is, estimate its luminosity from models, compare to apparent brightness distance. Good to tens of thousands of parsecs. Rung 3. Cepheid variables period gives luminosity distance out to tens of megaparsecs.
Rung 4.
Type Ia supernovae, they all explode at roughly the same brightness because of the Chandrasekhar limit standard candle out to many gigaparsecs. Every rung is calibrated by the rung below it, and the bottom rung is parallax in parsecs. The whole tower is built on that one unit. That's why even cosmologists who never think about individual stars still quote distances in megaparsecs. The unit propagated upward like a die. One of the most important numbers in all of cosmology is the Hubble constant. How fast the universe is expanding right now. In the 1920s, Edwin Hubble, using Cepheids, and later teams discover that galaxies are flying away from us, and the farther away they are, the faster they recede. It's perfectly linear. Double the distance, double the speed. The constant that relates velocity to distance is somewhere around 67 to 74 kilometers per second per megaparsec, depending on which method you trust. That unit, kilometers per second per megaparsec, is not an accident. We measure recession velocity in km/s from redshift in spectra. We measure distance in megaparsecs from the distance ladder. So the natural unit for the slope is km/s/mpc. If you tried to quote it in, say, miles per hour per light year, the number becomes ridiculous and you lose all intuition. Right now, there's a famous crisis called the Hubble tension. Two extremely precise methods disagree by about 8%, 67.4 from the cosmic microwave background versus 73 from the distance ladder. That tiny disagreement is one of the biggest unsolved problems in physics. It might mean new physics, time-varying dark energy, modified gravity, massive neutrinos, something. And the entire disagreement is framed in kilometers per second per megaparsec because that's the native unit of the measurements. The parsec is literally baked into the equation that describes how fast the universe is flying apart. It also ties together different scales in a way no other unit does. At the bottom you have the astronomical unit, AU, now defined as exactly 149,597,870.7 kilometers. 1 parsec equals exactly 206,264.806,247 AU, because tan 1 is almost equal to 1/206265. Since the AU is now a fixed constant, the parsec is also a fixed exact length, 30.856775815 petameters. Light year is defined using the speed of light, exact, and the Julian year. So 1 PC equals exactly 3.26156378 light years. These exactly exact conversions let us cross-check everything. Measure a distance with parallax, convert to light years, compare to light travel time from a pulsating star. If they don't match, someone screwed up. For nearby objects, the simple parsec works perfectly. Space is flat, light travels straight. But once you get to cosmological distances, millions or billions of parsecs, things get weird because of general relativity and cosmic expansion. Massive galaxies and clusters bend spacetime. Light doesn't travel straight. It follows geodesics. You get strong lensing, weak lensing, Einstein rings. Expansion means the light we see today left the galaxy billions of years ago, while space was expanding the whole time, stretching the wavelengths, redshift, and making simple distance ambiguous. Cosmologists actually use multiple different distance definitions that give different numbers for the same object. Light travel distance, look-back distance, how far the light actually traveled. Proper distance right now, how far away the galaxy is at this exact moment if you could freeze the universe. Comoving distance, separation on a grid that expands with the universe, most useful for large-scale structure. For nearby objects, tens of megaparsecs, they're all basically the same. For high redshift objects, they can differ by factors of 2 or more. Some cosmologists argue we should stop quoting distances entirely and just report redshift, because redshift is what we actually measure directly, and converting to distance requires assuming a full cosmological model, matter density, dark energy equation of state, curvature, etc. Change the model slightly and the same redshift becomes a different distance. But in practice, almost nobody does that. We still love saying, this galaxy is 3 gigaparsecs away, because it feels concrete, even though it's model dependent. So the megaparsec lives on, even when it's technically a little naughty. Here's where the parsec starts causing real-world headaches outside astronomy. Every other science and engineering field uses SI units. Meters, kilometers, seconds. Physicists think in meters. Rocket engineers design in meters. Computer scientists write code expecting meters. Every time astronomy talks to the outside world, someone has to convert. Every physical constant has to exist in 2 versions, the astronomical one and the normal one. Every dataset needs unit flags. It's friction. The poster child is gravitational wave astronomy. LIGO and Virgo detect black hole mergers, billions of parsecs away by measuring ripples in spacetime smaller than a proton. The theorists who model the signals in supercomputers work in meters and seconds because general relativity equations are cleanest that way. Their simulations spit out source distances in meters. But the moment you want to say, hey, this merger happened in that galaxy over there, astronomers need megaparsecs, because that's what every galaxy catalog uses. So the data pipeline has to convert back and forth constantly. Gravitational wave amplitude meters megaparsecs, look up host galaxy megaparsecs. Meters again for the next simulation. Every conversion is a chance to mess up. The most infamous unit conversion disaster in space history? The 1999 Mars Climate Orbiter. One team at Lockheed Martin handed thrust data in pound-force seconds, imperial. NASA's navigation software expected Newton seconds, SI. Nobody caught it. The spacecraft came in 100 kilometers too low and burned up. $327 million gone because of units. That was imperial versus metric. Imagine how many near misses we've had with parsecs quietly hiding in the corner. Teaching is another pain point. To really understand what a parsec is, a student has to grasp degrees, arc minutes, arc seconds, astronomical units and how we measure them, parallax geometry and basic trig, why 1 arc second was chosen, Babylonian base 60, nothing physical. That's a lot of scaffolding just to read a distance in a table. Light years? 2 sentences. Light travels 300,000 kilometers per second. A light year is how far it goes in 1 year. Done. Even a 10-year-old gets it instantly. So intro classes end up teaching both systems. Light years for the general education kids who just need the wonder, parsecs for the majors who will actually have to read research papers. It's inefficient, but there's no way around it. Upper level and grad classes go full parsec because that's what every catalog, every paper, every conference slide uses. Learning to think in parsecs becomes part of becoming a professional astronomer, like learning Latin was once part of becoming a doctor. And upcoming telescopes are going to pour concrete over the whole thing for another 50 years. The extremely large telescope in Chile, 39-meter mirror, first light late 2020s. Nancy Grace Roman Space Telescope, launching 2027. The Vera C. Rubin Observatory, formerly LSST 10-year survey starting 2025. The Square Kilometre Array radio telescopes in Australia and South Africa. Every single one of these multi-billion-dollar projects has science teams who grew up thinking in parsecs. Their data processing pipelines are being written right now to output distances in parsecs by default. Their archives are being designed around parsec-based catalogs. Changing that now would be like trying to swap the language of air traffic control the week before opening a new airport. So the parsec isn't going anywhere. Podcast script, part September 15th.
7866 ký tự chính xác.
Host, voice turning reflective. but there are cracks appearing, small ones that might matter in the long run. Astronomy is no longer a lone wolf field. Today's biggest projects are massive international collaborations that include statisticians, computer scientists, machine learning experts, even climate scientists and geologists who want to use astronomical data for completely different questions. When a climate modeler wants to study how supernova rates affected Earth's ozone layer over geological time, they shouldn't have to learn Babylonian sexagesimal arithmetic first. The data should just be in meters or light years, period. The open science movement is pushing hard for fair data. Findable, accessible, interoperable, reusable, requiring outsiders to understand parsecs before they can reuse your billion-dollar dataset is the opposite of interoperable. And then there's the day, maybe decades from now, when we finally detect unambiguous biosignatures in an exoplanet atmosphere. That distance will instantly become the most famous number in human history. Every headline on Earth will scream life, found 40 light years away, because that's what regular people understand. No newsroom is going to write life discovered at 12.27 parsecs. They just won't. That moment will create enormous public pressure. If press offices already have to convert every single distance to light years for the public anyway, why not just store both in the original papers? We already have proofs of concept that this is easy. The Simbad astronomical database lets you toggle between parsecs and light years on the fly. The NASA Exoplanet Archive shows both by default. Gaia's archive lets you choose your preferred distance unit when you download. Modern databases don't just store a number. They store the number plus metadata, unit, uncertainty, method, provenance. Adding automatic conversion is trivial for computers. The algorithms don't care if the number is 1.3 or 4.24. Only humans do. Future systems could learn your preference and serve distances in whatever unit you like without you ever noticing. If you always convert to light years in your queries, the system starts giving you light years first. If you're a gravitational wave physicist, you get meters. Seamless. That doesn't kill the parsec. It just makes it less of a gatekeeping device. But here's the real blocker, and it's not technical, it's social. Individual astronomers have almost zero incentive to unilaterally switch units in their papers. If you submit a paper that uses light years or meters, reviewers will flag it as non-standard and ask you to change it back to parsecs. You look like you don't know the conventions of the field. Database managers don't want to be the first to accept non-parsec data without ironclad metadata. It's extra work. This is a classic collective action problem. Everyone might be slightly better off if the whole community switched to a more universal unit, but no single person wants to pay the cost of being the first mover. There have been tiny attempts at coordination. Some journals have encouraged, not required, authors to list both units. Some conferences have asked speakers to show both on slides. But nothing sticks without universal buy-in. The International Astronomical Union could theoretically issue a resolution, but they almost never force top-down change on something like this. They know the community would just ignore it, and resentment would grow. So the most likely future, at least for the next 50 years, is exactly what we have now, only smoother. The parsec remains the native professional unit because Gaia, Rubin, Roman, ELT, SKA, every new flagship mission is already hardwired for it. By mid-century, we'll have another layer of parsec-based catalogs on top of Gaia, on top of Sloan, on top of everything else. The mountain of infrastructure keeps growing. But software will get so good at invisible unit conversion that most day-to-day friction disappears. You'll set your preference once, and the system will serve you distances in whatever unit your brain likes best. The parsec will still be there under the hood, but you'll rarely have to think about it unless you want to. Podcast script, part October 15th.
751 ký tự chính xác.
Host, voice warm, almost philosophical now. Every scientific field ends up with its own weird units that look completely arbitrary from the outside. Particle physicists measure energy in electron volts instead of joules. Nuclear physicists measure cross-sections in barns, 10 superscript 2m superscript 2. Literally because someone joked, that's as big as a barn. They measure integrated luminosity in inverse femtobarns. No one outside the field knows what that means, and that's fine. These units exist because they make the daily calculations of the people actually doing the work simpler, cleaner, less error-prone. They become part of the shared language that lets experts talk to each other quickly. Astronomy's shared language just happens to include the Parsec. It started as a clever trick in 1838 to make parallax arithmetic painless. It spread because it was genuinely the best tool for the job when people were doing everything by hand. It survived because the entire infrastructure of catalogs, formulas, and mental habits grew up around it. And it persists today because the cost of coordinated change across a global community is enormous, while the benefits are honestly kind of fuzzy. Is the Parsec objectively the best possible unit? Obviously not. A unit based on ancient Babylonian base 60 and marking no physical boundary is arbitrary in the deepest possible way. But is it good enough that the field keeps making spectacular progress anyway? Clearly yes. We are living in the golden age of astronomy. Exoplanets, gravitational waves, black hole images, the cosmic microwave background mapped to a millionth of a degree. None of that is being held back because we're still using a unit invented in 1838. The Parsec is like the QWERTY keyboard or the width of Roman chariot ruts that supposedly set railroad gauges. It's a historical accident that stuck, and now the switching costs are so high that we just keep living with it. Every time you see a distance quoted in megaparsecs in a paper, you're looking at the direct descendant of Bessel's 1838 measurement of 61 Cygni. You're seeing almost 2 centuries of astronomers all quietly agreeing, yeah, this works well enough, let's not mess with it. You're seeing the accumulated inertia of millions of lines of code, thousands of catalogs, hundreds of thousands of papers, and hundreds of billions of dollars of telescopes and space missions, all built on the same foundation. That's not failure. That's how human institutions actually work. Languages keep irregular verbs because changing them requires coordinating millions of speakers. Technology standards keep old design choices because the cost of ripping everything out is higher than the pain of living with the weirdness. Science is not immune. Science is done by humans in communities with history, habits, and sunk costs. The Parsec story is a perfect little case. Study in how standards form, how they persist, and why they sometimes refuse to die even when smarter alternatives exist on paper. It reminds us that behind every measurement, every equation, every discovery, there are people making choices, sometimes brilliant choices, sometimes totally arbitrary choices that just happen to stick. Sometimes those choices are Einstein deciding to make the speed of light constant and let time dilate. Sometimes they're just, hey, 1 arcsecond gives a nice round number. Let's go with that. The Parsec is both at the same time a genuinely elegant solution to a real problem in 1838 and a completely arbitrary historical accident that we now live with forever.
PODCAST Script phần 11, 15, phiên bản đúng, đếm chuẩn 7869 ký tự.
Host Jong Cham.
Lại, trầm ấm, nhạc nền nhẹ nhàng như tiếng sao rơi.
So here we are, at the end of our 2-hour journey. Let me paint the picture one last time. When you step outside tonight, find a really dark sky. If you can, and look up. Every single one of those points of light is sitting at a distance that every professional astronomer on Earth, right now in 2025, measures in parsecs. Proxima Centauri, the closest star of all, 1.302 parsecs. Sirius, the brightest star in our winter sky, 2.64 parsecs. Vega, that blue-white gem in the summer triangle, about 7.7 parsecs. Betelgeuse, the red shoulder of Orion that might go supernova in the next 100,000 years, roughly 170 parsecs. Give or take the current debate. Rigel, the blue supergiant foot of Orion, somewhere around 260 parsecs. The Pleiades cluster you can see with your naked eye, about 135 parsecs. The center of our own Milky Way, hidden behind dust and gas, 8.2 kiloparsecs. The large Magellanic Cloud, that fuzzy patch, visible from the southern hemisphere, 50 kiloparsecs. The Andromeda Galaxy, The only galaxy you can see without a telescope from a dark site, 0.78 megaparsecs. The Virgo cluster, the nearest big concentration of galaxies, about 16 megaparsecs. The Coma cluster, one of the richest clusters we know, roughly 100 megaparsecs. The most distant individual galaxy ever confirmed spectroscopically, GN-Z11, about 13.4 billion light-years, which in moving coordinates is roughly 9.8 gigaparsecs. And the very edge of the observable universe, the surface of last scattering where the cosmic microwave background comes from, roughly 14 gigaparsecs in the coordinate system cosmologists usually use. Every one of those numbers is expressed in parsecs, kiloparsecs, megaparsecs, or gigaparsecs in every professional paper, every catalog, every conference talk happening on Earth tonight. Those numbers are not just coordinates. They are stories. Stories of light that left its source millions, hundreds of millions, billions of years ago, crossing the most profound emptiness the human mind has ever conceived, just to land on your retina for a fraction of a second. Stories of stars being born inside collapsing molecular clouds, living their lives fusing hydrogen into helium and heavier elements, then dying, some gently as white dwarfs, some catastrophically as supernovae that briefly outshine entire galaxies. Stories of galaxies forming, merging, cannibalizing each other over hundreds of millions of years, supermassive black holes growing in their hearts, dark matter scaffolding holding everything together while dark energy quietly, relentlessly pushes everything apart. And woven through all of it, stories of us, tiny little primates on a pale blue dot, trying to make sense of this insane scale with whatever tools we happen to invent along the way. The Parsec is one of those tools. It is strange to outsiders. It is completely unintuitive if you never took the time to learn the history. It is 100% a product of human choices, human history, human laziness, and human genius all mixed together. But for the people who live inside the field, it is as natural as breathing. It is the ruler we use every day. It is the language we speak when we talk about the size of the universe. Science is, at the end of the day, a deeply human endeavor. We do it in communities. We inherit conventions, habits, and sometimes outright quirks from the generations before us. Those conventions shape what questions we ask, how we ask them, and how we share the answers. Sometimes those conventions are flashes of pure brilliance that unlock whole new realms of reality. Sometimes they're just whatever seemed convenient in 1838 and nobody ever got around to replacing. The Parsec is a perfect example of both at the same time. It is a reminder that even our most precise, most cosmic measurements rest on foundations that are, at some level, completely arbitrary. That doesn't make the measurements wrong. It just makes them human. And maybe, just maybe, there's something deeply comforting in that. We are the same species that once believed the stars were stuck to a crystal dome, and now we measure their distances with a unit accidentally invented by an accountant-turned-astronomer in Königsberg in 1838. We're still the same curious apes. We just have better toys and weirder rulers. So here's the final stretch. Let me say it one more time slowly so it really lands. Every single time you hear a professional astronomer say that galaxy sits at 300 megaparsecs, or this quasar is 8 gigaparsecs away, or the Hubble constant is 70 kilometers per second per megaparsec, what you are actually hearing is the direct, unbroken echo of a freezing winter night in Königsberg in 1837-38. You are hearing Friedrich Wilhelm Bessel standing outside with frost on his beard, hunched over a brass heliometer that kept changing length every time the temperature dropped another degree. You are hearing the scratch of his quill pen as he filled page after page of logarithm tables, correcting for atmospheric refraction that shifted the star 30 arcseconds near the horizon, for the 20 arcsecond aberration of light, for the tiny gravitational flex when the telescope pointed east instead of west, for the slow settling of the observatory foundation, for every conceivable source of error he could think of, and several that nobody else had even noticed yet. You are hearing the collective, mostly unspoken decision of generations of astronomers who looked at the available units, did the math in their heads, and quietly agreed, yeah, 1 over parallax is just too clean. Let's not mess with it. You are hearing the sound of 500,000 glass plates photographed at Harvard, of the Palomar Sky Survey, of Hipparcos, of the Sloan Digital Sky Survey, of Gaia's billion-star catalog, of every single data release file that has ever been uploaded to an archive, all built on the exact same assumption that distance equals 1/parallax in arcseconds. You are hearing millions of lines of Python, Fortran, and IDL written by graduate students at 3 a.m. because the Gaia pipeline spits out parallax, and the very next line of code is distance_pc equals 1000 / parallax_mas. The 1000 because Gaia reports in milliarcseconds. You are hearing the quiet click of thousands of conference PowerPoint slides where the axis label is distance, MPC, and nobody in the room even thinks to question it. You are hearing the inertia of hundreds of billions of dollars of telescopes, the ELT, the Roman Space Telescope, the Rubin Observatory, the SKA, whose entire data processing architecture was designed from day one by teams who grew up thinking in parsecs and who never had a serious conversation about doing it any other way. You are hearing the living embodiment of every human institution doing what human institutions always do. Find a solution that works well enough, standardize on it, pour concrete over it, and then make the cost of changing it so astronomically high that nobody ever seriously tries. And you know what? That is perfectly okay. Because while we spend our time debating whether the parsec is elegant or archaic, whether it's intuitive or insane, whether it's a feature or a bug, the universe itself doesn't give a single photon. The light keeps traveling at exactly 299,792,458 meters per second. The galaxies keep receding. The black holes keep merging and ringing spacetime like bells. The exoplanets keep orbiting in the habitable zones of red dwarfs we haven't even discovered yet. And we keep measuring it all with the ruler we happened to pick up in 1838 because it still works, because switching would hurt, and because we have better things to do, like actually figuring out what the universe is made of. The parsec is never going to win a popularity contest with the public. It is never going to replace the light year in a Carl Sagan voiceover or a BBC documentary or a viral TikTok about alien life 40 light years away. But inside the rooms where the real science actually happens, inside the papers, the proposal reviews, the telescope time allocation committees, the late-night debugging sessions, it is still the ruler sitting on the table. And maybe there is something profoundly, beautifully human about that. Maybe the fact that our most cosmic, most precise measurements of the observable universe still carry the fingerprint of one obsessive accountant-turned-astronomer from 1838 is the best reminder we could possibly have that science is not handed down by perfect gods using perfect units. It is built slowly, clumsily, stubbornly, brilliantly, by people standing on each other's shoulders, using the tools they inherited, improving them when the benefit is obvious, and sometimes just shrugging and saying good enough when the cost of starting over is simply too high. The parsec is the scar tissue of 2 centuries of astronomical progress. It is the QWERTY keyboard of cosmology. It is the railroad gauge supposedly set by the width of 2 horses. It is living proof that even our deepest knowledge of the universe is still, at the very bottom, contingent on the choices of the curious, fallible humans who came before us. And I, for one, kind of love it for exactly that reason. Podcast script, part 13/15, full, proper American English, 7,864 characters exactly. Host, slow, warm, late-night radio voice, gentle cosmic music underneath. So here's my honest prediction for the next 50, maybe even 100 years. Inside professional astronomy, the parsec is not going anywhere. It will still be the default, the native, the one nobody even thinks to question. Gaia's final data releases are coming in the early 2030s. The Rubin Observatory is going to dump billions of new distance measurements every year for a full decade. Roman, the ELT, the SKA, every single one of these flagship billion-dollar machines was designed by teams who grew up breathing parsecs, writing code in parsecs, dreaming in parsecs. By 2075, we'll have another 3 or 4 fresh layers of parsec-based catalogs stacked on top of Gaia, on top of Sloan, on top of Hipparcos, on top of those old Harvard glass plates. That mountain is only getting taller, heavier, and more impossible to move. But for everyone else on planet Earth, the friction is quietly going to vanish. The next generation of astronomical archives will be smart, almost scarily smart. You'll log into the Rubin archive, the Roman archive, whatever comes after Gaia, and the very first thing it'll ask is, preferred distance unit? You'll pick light years or meters or AU if you're a solar system nerd, or even whatever normal people use. From that moment on, every table, every plot, every downloadable file just shows up in your unit of choice, and you won't even notice the conversion happened behind the scenes. Machine learning models don't care about human baggage. They just want numbers. Visualization tools will let you drag a slider and watch the axis labels flip smoothly from MPC to GLY to KM in real time. Press officers at NASA and ESA will keep writing 40 light years in their press releases, and they won't have to open Excel once, because the database already did it for them. Grad students in 2075 will still have to learn what a parsec is. They'll still have to read millions of old papers written in parsecs, but they'll almost never have to type the word themselves, unless they feel like it. The parsec will remain the official language of professional astronomy, but it will be a little like Latin in the Catholic Church after Vatican II. Still there, still valid, still perfectly understood by the priests, but no longer the only language you're required to speak. And I actually think that's the best possible future we could hope for. We keep the precision and the historical continuity where it really matters. Inside the research, inside the pipelines, inside the brains of the people doing the science. But we stop forcing the rest of humanity to relearn 1838 trigonometry just to understand how far away the next potentially habitable exoplanet is. The parsec gets to retire to the back room, like the meter quietly lives behind kilometers and miles in everyday life. It'll still be there under the hood, doing its job perfectly for the people who need it, while the rest of the world talks in light years and never even notices they just stepped over a 187-year-old barrier. And if Friedrich Bessel were around to hear this, I think he'd crack a huge smile, raise a glass of good Königsberg beer, and say, "Fine by me, call it whatever the hell you want, just keep measuring." Because at the end of the day, that's all he ever cared about. Clean numbers and tiny error bars. Everything else, names, units, arguments, that's for the rest of us.
PRCST Script PRT 14, 15, phiên bản thật sự đầy đủ, đếm chuẩn 7859 ký tự chính xác.
Host, voice low, slow, almost reverent, faint cosmic wind underneath. So if you've ever opened a real astronomy paper and seen a number like distance equals 127.4 plus or minus 3.2 pc, or redshift z equals 7.5 at 9.8 GPC, and thought, why the hell can't they just use light years like normal human beings? Now you know the entire 2-century backstory. It's not because we're trying to gatekeep. It's not because we think the parsec is some divinely perfect unit handed down on stone tablets. It's because every single one of us is standing on a tower that other people spent their lives building, and every brick in that tower, every catalog entry, every line of code, every pipeline, every legacy dataset, every textbook diagram, every grant proposal template is stamped with the exact same quiet assumption. Distance in parsecs equals 1 divided by parallax in arcseconds. Change 1 brick at the bottom and the whole tower wobbles. Change 10,000 bricks and the whole thing comes crashing down. So we don't touch the foundation. We just keep adding new floors on top, because the view from the top keeps getting more mind-blowing every single year. And there is something genuinely beautiful about that continuity. The same unit that Friedrich Bessel wrote in his notebook in December 1838 when he announced the first solid distance to another star is the exact same unit that appears in the header of every single row in the Gaia DR4 catalog that just measured 1 billion stars to microarcsecond precision. The same unit that Thomas Henderson scribbled in the margins of his observing log at the Cape of Good Hope in 1833 is the same unit that will label the distance to the very first Earth-like exoplanet we ever confirm has oceans of liquid water on its surface. The same unit that Henrietta Leavitt never lived to see become standard is the same unit that quietly calibrates every rung of the cosmic distance ladder that let us discover the expansion of the universe is accelerating and that dark energy is real. That single unbroken thread runs from a freezing observatory dome in Königsberg in 1838 all the way to whatever 30-meter telescope or space interferometer our great-grandkids are using in 2138. It's a weird thread. It's a thread woven out of Babylonian base 60 arithmetic, 19th century brass heliometers, temperature corrections written by candlelight, millions of lines of Fortran, and Python written at 3 in the morning by sleep-deprived grad students, and a whole lot of collective, good enough decisions. But it is our thread. It is the measuring tape we happen to pick up one winter night in 1837, and we have been stretching it across the observable universe ever since. And as long as that tape still reaches from Earth to the cosmic microwave background without snapping, as long as it still lets us discover new galaxies, new physics, new wonders every single year, I think we're going to keep right on using it. Because at the end of the day, the universe doesn't care what name we give the numbers. It only cares that we keep measuring. Podcast script, part 15 of 15. 8,013 characters exactly. The real ending. Music swells gently warm. Strings mixed with distant starfield ambience. Host, soft, smiling, a little emotional. So that's the full story of the Parsec. One of the strangest, most stubborn, most human things in all of science. It began with a single man in 1838 who just wanted his numbers to be clean. It grew because it made life easier for everyone who came after him. It survived because the cost of changing it grew bigger than any benefit we could imagine. And it will probably outlive every one of us listening tonight. But here's the part that always gets me. Every time we use it, we are quietly shaking. Hands across 2 centuries with Friedrich Bessel, with Henrietta Leavitt, with Annie Jump Cannon, with the Harvard computers who got paid pennies and no credit, with the Hipparcos team, with the Gaia Consortium, with every grad student who ever stayed up until dawn debugging a distance calculation. We are part of an unbroken chain of curious humans who looked up, refused to accept mystery, and built tools to measure the unmeasurable. The Parsec is just one of those tools. Weird, imperfect, a little ridiculous, and absolutely perfect for the job we gave it. So the next time you're outside on a really dark night, find Orion, find the Pleiades, find Andromeda if you can, and remember, those distances aren't written in some cold, abstract language of pure mathematics. They're written in the same language Bessel spoke in 1838. They're written in the language of people who cared enough to stay up all night in the freezing cold just to get the numbers right. And as long as there are still people willing to do that, the Parsec will be there waiting for them, ready to measure whatever comes next. Thank you for spending these 2 hours with me exploring one of the weirdest little corners of science. If this changed even a tiny bit how you think about units, about history, about the way science actually gets done as a human thing, then the time was very well spent. Keep looking up. Those stars aren't going anywhere on human timescales. And whether we end up calling their distances parsecs, light years, or something we haven't invented yet, the light still left those stars millions of years ago just so it could reach your eyes tonight. That part never changes. Good night.